In this video, we solve another example problem using the method of undetermined coefficients. This was modified from problem number 26 in section 4.4 of a first course in differential equations by Zill, 9th edition. The problem 26 actually looked like this, but I just realized that I hadn't shown you any with trig functions on the right-hand side, so I just added that sine of x. It's probably going to make the coefficients a little bit uglier. We might see some fractions that might make us worry because I just invented that problem on the fly. But the method should still work. I just want to show you how to handle coming up with the right y sub p if the right-hand side has a trig function. So this is the differential equation, and let's first verify that the method of undetermined coefficients is appropriate. Now remember, when you're deciding whether or not you can use this method, you have to look at the corresponding homogeneous equation, and then you have to look at the form of the right-hand side. So the corresponding homogeneous equation looks just like this, but the right-hand side is 0. So I ask myself, does this equation have constant coefficients? And it does. The coefficient here is 1. The coefficient over there is just -1. Since the differential equation has constant coefficients, the corresponding homogeneous equation has constant coefficients. The guessing method, which is the method of undetermined coefficients, is appropriate so far. And then we also have to check the form of the right-hand side. Now, the right-hand side has to be either a polynomial, an exponential function, a sine or a cosine function, or some finite product or sum of those. And this is a linear polynomial. This is a product of a linear polynomial and e to the negative x. And that is a sine function. So that condition is satisfied. We can make an educated guess for y sub p, and since derivatives of linear polynomials give you linear or give you lower degree polynomials or constants, and since polynomials times exponentials will give you polynomials times exponentials back, and since sine and cosine of x, the derivatives of both of those functions give you sine of x if you take the derivative once or twice, depending on whether you're dealing with sine or cosine, or 3 or 4 times like we will in this case. This linear combination of those functions could potentially give us this function over here. So the right-hand side is of the appropriate form. It's the sum of a first-degree polynomial and a first-degree polynomial times an exponential. And a sine function. So the guessing method will work. Now, always check this first. If the coefficients over here depend on x or t, or if the right-hand side doesn't have the right form, this method is no longer appropriate. But this time it is. So we'll start by solving the corresponding homogeneous equation. Now, whenever you're solving a constant coefficient, a homogeneous linear differential equation, we'll always let y equal e to the mx to start. Because derivatives of exponentials give you other exponentials, and for the right exponential, those will cancel out and we'll get a 0. And we'll take the first, second, third, and fourth derivative because this is a fourth order differential equation. Derivative of e to the mx is e to the mx times the derivative of the inside, which is an m. Take the derivative again. By the chain rule, you just get another m. Take the derivative again. By the chain rule, you get another m. Finally, the fourth derivative, you have 4 m's out front, multiplying each other. So I want to compute all of those guys, and then we want to substitute into the differential equation. And we're substituting into that homogeneous differential equation right now, this one. So after our substitution, this is EQN, an abbreviation for equation. The fourth derivative goes here. And then we're subtracting the second derivative. And we want that to equal 0. And that's equivalent to this. Factor out the e to the mx. And the e to the mx is never 0, so we get this characteristic equation. Okay. Now you want to solve the characteristic equation for m. It's a fourth degree polynomial, but this one's actually really easy to solve. We don't need possible rational roots or anything like that. If I factor out an m squared, this becomes m squared times m squared. M squared times m squared gives me m to the fourth, and m squared times -1 would give me that m squared. And then this is a difference of squares. Remember that? Remember, if you've got a squared minus b squared, that factors to a plus b times a minus b. This is m squared times m plus 1 times m minus 1. Okay, so it looks like we've got this is a factored form of our characteristic equation. This times this equals 0 if this factor equals 0, or this factor equals 0, or this factor equals 0. So the only way we're getting 0 out of that product is if one of the factors is 0. Obviously, m is equal to 1 here. Be careful though, this is not a single root. Since that m is squared, this tells us that two values of m, m1 and m2, are both equal to 0. That's a repeated root. So we're going to have two linearly independent solutions to the differential equation that correspond to m equals 0. And then over here, if you subtract 1 from both sides, you get m equals -1. That's going to be our m sub 3. And if we add 1 to both sides, we get m sub 4 equals +1. So the two linearly independent solutions that come from this are y1 equals e to the m1x, and y sub 2 equals e to the m1x times an extra x. And that extra x, we could prove that that works using reduction of order. We could prove that, well, that x should be there using reduction of order. That's where that x comes from. Now in this case, m1 and m2 are both 0, so this is just e to the 0x. So y sub 1 equals 1 is a solution of the differential equation. And here I've got e to the 0x times x, which is just an x. Over here, our solution that corresponds to m sub 3 equals -1. That's e to the -1 times x. And the solution that goes with this is e to the +1 times x. So the solution to the general solution to the corresponding homogeneous equation is called y sub c. That's the complementary function or the complementary solution. It was a fourth order differential equation. So it's c1y1 plus c2y2 plus c3y3 plus c4y4. If it's fourth order and you only have 3 solutions, and a lot of students will get 3 solutions from this, you know you did something wrong. And it's usually something like this. If that factor is raised to a power other than 1, that's a repeated root, and you get more than one linearly independent solution from that. In our case, y sub 1 was just 1. Y sub 2 happened to be x. Y sub 3 was e to the -x, and y sub 4 was e to the x. So we found our characteristic equation. We factored it. We solved for m1, m2, m3, and m4. And then we state those four solutions, y sub 1, y sub 2, y sub 3, and y sub 4. And then we have y sub c here. That's c1, y1 plus c2, y2 plus c3, y3 plus c4, y4. Okay, we're done with that part. Now let's go back to the original differential equation. And I will apologize in advance. Our coefficients are going to be ugly because this is not a textbook problem. This is a problem I modified from a textbook problem. So the constants are probably going to be some unexpected or fractions. Maybe they are expected because I made this up myself. Okay, so we look at the right-hand side and we use the right-hand side to determine the form of y sub p. So first we just write down the educated guess based on the form of the right-hand side. Now the right-hand side is a linear polynomial. So I would guess that y sub p is a linear polynomial. And then that's just for this term. Then for this term, I would guess that y sub p is a linear polynomial times e to the negative x. And for this term, I would guess that since I've got a sine of x here, that y sub p is a constant times sine of x plus a constant times cosine of x. Okay, now for each of these parts, we have to look at the parts, look at each guess separately. Remember, this guess goes with this function, and this guess goes with this function. And this part of the guess goes with this part of y sub p. Now, if we have to modify these, we modify them separately. If this requires modification, we'll multiply by x as many times as necessary so that these terms aren't a part of y sub c. Similarly, if this doesn't work, because there are some terms here that are part of y sub c, we'll modify this guess until we have no terms that are part of y sub c. And the same is true for this guy. But you want to handle this guess, this part of the guess, this part of the guess, and this part of the guess separately because they correspond to different terms on the right-hand side. That's all having to do with that superposition principle for non-homogeneous differential equations that we talked about when we talked about preliminary theory for higher order differential equations. Okay, so this would be our preliminary guess. Just looking at the right-hand side, this is what I would guess. But now if I want to get the right guess, I want to get a guess that will work, I need to look at all of these terms and compare them to the terms up here. I ask myself, will ax plus b work? No. If I plug in ax plus b here, ax plus b is actually already part of y sub c. A constant plus a constant times x actually solves the homogeneous differential equation. So if I plug this in here, I'm not going to get a 4x, I'm going to get a 0. So I need to multiply this by an x. But then what am I left with? I'm left with an ax squared, which is fine because I don't have a constant times x squared up here, plus a constant times x. But a constant times x won't work because a constant times x is a solution to the corresponding homogeneous equation. So I need to multiply by x again. Now distribute, think about what will happen. X squared times ax is going to give me an ax cubed. And there's no ax cubed up here, that's good. And b times x squared is not up here either, so that's good. So that's going to work. So this is the modified guess. After I distribute, I'll have ax cubed plus bx squared that corresponds to that 4x on the right-hand side. Okay, so now let's look at this guy. I've got a constant times x times e to the negative x. That's not up here anywhere, so that should be fine. Plus a constant times e to the negative x. Ooh, there is a constant times e to the negative x here. So that's actually not going to work. So I need to multiply this by an x. Just put it in there because it's There's not enough space. I should have left myself more space. Now I ask myself, if I distribute this x times cx would give me cx squared times e to the negative x. And there's no constant times x squared times e to the negative x up here, so that'd be fine. And then I have a constant times x times e to the negative x. And there's no constant times x times e to the negative x up here. So that's going to work just fine. So I will distribute that x now. And then for this guy, I say, is there a constant times sine of x in y sub c? There's not. Constant times cosine? There's not. So we'll just keep those guys around. Wow, this is going to be a huge system of equations. But it should be okay. We'll be able to solve it. No big deal. Just a lot of differentiation to do and a little bit of a product rule there. Okay, so you find your educated guess and then you modify it by multiplying by x where necessary so that the guess that goes with a particular term in that right-hand side of the differential equation does not appear in the y sub c. Because if that term appears in y sub c, that means that that expression will not give you this function that we want on the right-hand side. If you plug it in over here, you're going to get a 0. And remember, that's what y sub c is. We're looking for a function that you can plug in over here and you'll get this. Y sub p is the solution that satisfies this equation, the function that you can plug in that will give you this. So if the guess is up here, it won't give you that. So you multiply by x until the guess is not there. I know that can be a little confusing. Text me if you need help with that, or you can send me an email as well. So we come up with our very much educated guess for y sub p. And it was a fourth order differential equation. So we're going to take the derivative of this 4 times and substitute into the differential equation. So we're going to be here a while. It's no big deal though. Most differential equation students need a little practice with differentiation even after 3 semesters of calculus. A little practice won't hurt us. So we'll take the first derivative. Derivative of ax cubed is 3a times x squared. Derivative of bx squared, you bring the b down. Derivative of x squared is 2x. And then here we've got to use the product rule. It's my first function. There's my second function. According to the product rule, we'll get the derivative of the first times the second plus derivative of the second. Derivative of e to some power is e to that power times the derivative of the inside times the first. Derivative of sine of x is cosine of x. Derivative of cosine of x is negative sine of x. Okay, now these two terms here, it's helpful to combine them. That way we don't have to do the product rule for this and this, we'll just have to do the product rule once if we combine them. So y sub p prime is 3a squared plus 2bx, and there should be a negative there, plus e to the negative x times something. So I get a d from here, it's the constant term, and then I have 2cx and a negative dx. So this is 2c minus d times x. And notice I'm collecting like terms in x. I've got a constant, and then I wanted the constant times x. And then the last part I want is that constant times x squared. I have a negative 1 times that constant times x squared. So this is negative c x squared. Don't forget your cosine and sine functions. Okay. Now it was a fourth order differential equation, so you keep taking derivatives. So second derivative of this is 3a times the derivative of x squared, which is 2x. So I'll get 6ax. Here I've got a constant times x, so I'll bring down my constant. Over here, product rule again, derivative of the first times the second plus derivative of the second times the first. Derivative of d is 0. Derivative of this constant times x is just the constant. Derivative of negative cx squared is minus 2c times x. So it's derivative of the first, multiplied by the second. Then we add the derivative of the second. Derivative of e to the negative x is e to the negative x times the derivative of the inside times the first. Okay, and then the derivative of cosine of x is negative sine of x. Derivative of sine of x is cosine of x. And again, we want to take these two pieces, I'm going to put them together. I'm going to write that as a single term. So we have 6a times x plus 2b. And I want this to be a product. I want this to be a polynomial times e to the negative x. So for the constants, I've got negative 2c, or excuse me, positive 2c minus d minus another d. So that will be 2c minus 2d is my constants. And then I have minus 2cx here, minus 2c minus a minus d. So it's going to be plus d. So minus 2c is minus 4c plus d times x. Then we've got a negative times a negative cx squared is a positive cx squared. And we bring down that negative f times sine of x and the negative x, or negative g times cosine of x. Woo, second derivative, third derivative. Keep going. Derivative of a constant times x is just the constant. Derivative of the constant is 0. Product rule. You're probably tired of the product rule. You're going to be so good at the product rule after this class. Oh my goodness. Okay. So we have derivative of the first. Derivative of a constant is 0. Derivative of a constant times x is just the constant. Derivative of this constant times x squared is c times 2x. So it's derivative of the first times the second, plus derivative of the second times the first. Oh, and there's so much. I'm just going to call it first for right now. Derivative of the second is that negative e to the negative x again. And then we have this derivatives of these pieces. Derivative of sine is cosine. Derivative of cosine is negative sine. Negative sine times that negative is going to give me a positive sign there. Okay. And we are here again, it makes sense for us to collect like terms here. So we've got 6a plus. Okay, now I want all the constants. So I've got negative 4c plus d, and then I have a negative 1 times this. So negative 4c plus d minus 2c plus 2d. Negative 4c minus 2c is negative 6c. And d minus a negative 2d, that's d plus 2d, is going to be 3d. Okay, so we're there. And then we're adding the x terms. So I have 2c times x here, and then I'm subtracting negative 4c plus d times x. So I have 2cx minus a minus 4c, so that's 2cx minus minus 4c is adding 4c, so it's going to be 6c times x minus d times x. And then the x squared terms is that negative 1 times the cx squared that would be right there if I had written it down. So negative cx squared goes here. Okay. Plus this function, not changing them at all. Fourth derivative. Derivative of that constant is 0. Here I need the product rule. There's my first function and there's my second function. According to the product rule we get derivative of the first. Derivative of a constant times x is the constant. Of course, the derivative of the constant is 0. Derivative of negative cx squared is negative 2c times x. It's derivative of the first times the second plus derivative of the second times the first. Okay, that's from there. And then we have to add the derivatives of the sine and cosine terms. Derivative of cosine is negative sine. Negative times a negative is going to make that a positive f times sine of x. Derivative of sine is cosine. It's a lot of differentiation. Now, you got to remember what it was we were doing. Trying to solve a non-homogeneous differential equation. So I want the fourth derivative of y sub p minus the second derivative of y sub p to equal this function over here. So I'm going to subtract these two functions vertically. I'm going to add like terms in columns, and then we'll find out what system of equations A, B, C, D, looks like I skipped E, F, and G need to satisfy. So let's do that now. Oh, I guess we should simplify this. So I've got a constant, C or 6c minus d, and then I'm subtracting negative 6c plus 3d. 6c minus a negative 6c is 12c. And I've got a minus d and a minus 3d from there, so that's minus 4d. Okay. And then I have a negative 2cx here, and I'm subtracting 6c minus d times x. So I have negative 2c minus 6c, so that's negative 8c, minus a negative d, so that's plus d times x. And then the x squared term is a negative times a negative 6, or negative cx squared. That's going to be a positive cx squared times the exponential, plus f times sine of x, plus g times cosine of x. And now we want to add these like terms in columns. Now I don't even know if I have enough room on my paper to do that. So I think I'm just going to flip the paper over and save this little bit of space for scratch paper for some other problem later. Okay, but this is my fourth derivative. I need that. Remember, a differential equation looks like this. So I need the fourth derivative, and I'm subtracting the second derivative, and I want it to be equal to this right-hand side. So first I'll write down the fourth derivative, and I will add vertically. So I've got this constant plus this constant times x plus a constant times x squared times the exponential plus f times sine of x plus g times cosine of x. That's my fourth derivative. Then I'm subtracting the second derivative of y sub p, which was this guy right here. So basically what I'm doing is I'm going to multiply each of these terms by a negative 1. So I'll have a negative 1 times ax, and I don't have any other terms like that. Or I said negative 1 times ax. Negative 1 times 6ax, so it's negative 6ax minus 2b. And then I want this times -1. So that's going to give me a -2c plus 2d, 4c minus d, and a minus c times x squared there. And then we're multiplying this by -1, so it's a positive f times sine of x, and a positive g times cosine of x. Then we add all of these together, and that's a simplified version of the left-hand side of that differential equation. So I end up with 10c here, minus 2d. These guys reduce. And then you have a -4c times x. And then these guys reduce. All of these are multiplying that e to the -x. And then I've got 2f sine of x plus 2g cosine of x minus 6ax minus 2b. And we're setting this equal to the right-hand side of that differential equation, which was this. 4x, and I'm lining up those like terms. And then I had a 2x e to the -x. Just adding that so that the form matches. And then a single sine of x. Now I don't have any cosines over here, so I'll add a 0 times cosine of x. And I don't have any constant terms, so I'll add a 0. And I don't have a constant times e to the -x, so I'll add a 0 over here as well. Now, because of the linear independence of sine, cosine, x, 1, x times e to the -x, and e to the -x, the only way this left-hand side equals this right-hand side is if the corresponding coefficients are equal to each other. So we end up with this system of equations. It's a system of equations with, what, 6 unknowns? We had 6 unknowns, but it's going to be such a simple system of equations to solve that we can solve for all 6 of them. So first we'll have 10c minus 2d. That has to be 0. And -4c must be equal to 2. Here, 2f must be equal to 1. Here, 2g must be equal to 0. And here we've got -6a equals 4 and -2b equals 0. So this is a really nice, very easy to solve system. I can take this and I can divide by 2 immediately. I get 5c minus d equals 0. So d will equal 5 times c, and I can find c from right here. So from this one, if I divide both sides by -4, I'll have c equals 2 divided by -4, or -1/2. C equals -1/2, and we take 5 and we multiply by -1/2, we get -5/2. Okay, over here, f is 1/2. The only way that 2 times g equals 0 is if g equals 0. Here we have a equals 4 divided by -6, or -2/3. And lastly, we get b equals 0. Whew, that's a lot, but it was actually really easy to solve. So y sub p equals this. Remember this guess from a long time ago? It's equal to this, where a, b, c, d, f, and g are the values on this list. So a was -2/3. So we have -2/3. That was our a times x cubed. Plus b times x squared, so we have 0x squared, it turns out. Plus cx squared, so that's -1/2 x squared, plus dx, that's -5/2 x, times the exponential, plus f times sine of x, so that's 1/2 times sine of x, plus g times cosine of x, which was 0. So that is our y sub p. And we're not finished yet. We always want to find the general solution. General solution is y equals y sub c plus y sub p, and y sub c is C1 plus C2x plus C sub 3 times e to the negative x plus C sub 4 times e to the x. That's our y sub c, and then we add y sub p. This works for all real numbers. Okay, so let's go through the method one more time. What did we do? The first thing we did was we said, okay, does this method even work for this? It does, because if I set the right-hand side equal to 0, my corresponding homogeneous equation is this, and it has constant coefficients. So that criterion is checked off. We're good with that. Now we need to look at the right-hand side, and we say the right-hand side is a sum of a polynomial, an exponential function, a sine or cosine, or a product of those. Turned out to be a sum of this guy, and this one happened to be a product of a polynomial and an exponential. So the right-hand side has the right form. The left-hand side has the right form. So we can use this method. The first thing we do every time is we solve the corresponding homogeneous equation, because that's going to help us to modify our guess for y sub p. So we solve the homogeneous equation by letting y equal e to the mx, substitute into the equation, you get your characteristic equation. We solve for m. This time it was pretty easy, you just factored. And then you've got, since it was a 4th degree characteristic equation, you have 4 solutions, m1 through m sub 4. One happened to be repeated. And once you have that repeated root, you get 2 solutions there. The first one is e to the m1x. The second one is e to the m1x times an extra x. That's what we do every time we have a repeated root. Then you have the e to the m3x and e to the m4x there. And then y sub c is just what you get when you take each of these 4 functions. You multiply them by constants, you add them together, and that's your complementary function. And then you say, okay, let's look at the non-homogeneous part. I want to find the solution for this. Because the right-hand side is that combination of polynomials, exponentials, sine and cosine that we talked about. It's a sum, and then this one happens to be a product. We guess that y sub p has the same form as that right-hand side, and then we look at each guess, each of them separately, and you say, is there any term here in this guess that goes with that 4x that is also up here? And we said yes. So we had to multiply by an extra x, but then we still had a constant times x up down here, which would give us that constant times x up here. So we had to multiply by an x again. So we had to multiply by an x squared on this guy. On this one, we ask ourselves, if we distribute that e to the negative x, is there any term here that's also up here? And that constant times e to the negative x was right here, constant times e to the negative x. That would have given us a 0 if we substituted into the left-hand side of the differential equation. So we said, multiply by an extra x, and you won't have that problem. This times this is not up there. This times this is not up there, so we're good. And then we looked at these guys, and we said, there are no sines or cosines over here, so we can leave that part of the guess alone. And we said, okay, let's try this, and let's find the values of a, b, c, d, f, and g that will cause this function to satisfy this equation. So we had to take a bunch of derivatives. And we spent the next page computing derivatives. After you've made that educated guess, it was a 4th order equation, so you had to find y sub p prime, y sub p double prime, y sub p triple prime, and then the 4th derivative of y sub p, our potential y sub p, our guess for y sub p. And then we said, okay, if this satisfies the differential equation, then if I substitute into the differential equation, I should get an equation that's true. So we substitute y sub p double prime and the 4th derivative of y sub p into the differential equation. And then you set the left-hand side, once you simplify, equal to the right-hand side. And I'm choosing to add vertically just because it helps with the bookkeeping. It helps me to make sure that I don't lose any terms if I do it that way. Okay, so we get this, and then we say, the only way the left-hand side equals the right-hand side is if the corresponding coefficients are equal, and that has to do with the linear independence of the functions. So we said, this has to equal this, this has to equal this, this has to equal this, and so on. So it's a system of 6 equations with 6 unknowns, but it was really easy to solve because they were uncoupled. each of these you could solve without even referencing the other equations. And then once we had C, we were able to use C to find D. Okay, and then we said, if that's true, then this equals this. And if this equals this, then that means y sub p has this form. So we took the values of A, B, C, D, F, and G. And I'm just going to say solve for the constants because I left out that E, and it's sort of hard for me to remember that I left out that E. And then you substitute those into the form of y sub p. And then once you have done that, the general solution is y equals y sub c plus y sub p. And that's true on the entire real line. If you wanted to, you could take the derivative of this 4 times, substitute into the differential equation. You would find that this actually works. If you do that, you're going to get this on the right-hand side.